So today we're going to cover the rest of memory-centric computing. And there's a lot more to cover here, but we just don't have enough time. And then I hope to at least start memory robustness, because if we start today, then we have a chance of finishing tomorrow. If we don't start today, then we probably won't finish it tomorrow. There's a lot to cover over there too. And probably, I don't know if we'll get to topic 4, which was planned, but we'll see. Okay, remember we're talking about processing in memory. We were talking about processing using memory, processing near memory. We talked a lot about processing using memory. And I believe Giovanni later today is going to talk about bit-line computing in SRAM, which is a version of processing using memory. He may be adding near memory logic also, who knows. So I'd recommend you take a look at this course. So processing near memory. We were covering a lot of things. And as I said, we're not going to cover everything, but today we're going to cover some more, and then we're going to talk about some adoption challenges. And we were thinking of memory as an accelerator. And remember, the last thing we covered was in-storage acceleration of genome analytics. And this was the paper we covered, GenStore. It was an ASPLOS 2022. I just want to spend a little bit more time on this because I think this is another area that's extremely important. I believe it's going to be a lot more important into the future. Genomic analyses, in general, omic analyses, like biological sequence analyses that are going to be more important to the future. And this is one of the very, let's say, hot off the press works that we did. It was published in July in ISCA. I'm going to very quickly give an overview of it. As I said, metagenomic analysis is analysis that you do on samples that you don't know. You don't know what's there in the sample that you've taken, and you want to identify the samples. And this design is, again, a hardware algorithm co-design, where we design in-storage processing for metagenomic analysis, and we don't do everything in storage. We really partition things across storage system and the host system, as you can see over there. I don't know why the colors are so bad here. In the slides, you will see them better. Not in the printed version. Printed version doesn't have colors. Yeah. So these are the 3 steps of metagenomic analysis that we want to really accelerate. You basically have a metagenomic sample with species that you don't know in advance. So you prepare them. You basically sort these queries in somehow. And then you compare these k-mers to k-mers are basically sequences, base pairs of length k, essentially. That's what a sequencer does. A sequencer chops your genome, or something's genome, into sequences that are of length some number. In this case, we're assuming k. And then you basically compare it to a huge database to identify what kind of species are lurking there. And then you can also estimate the abundance of those species in some ways. And these are actually pretty data-intensive tasks. This is really a hardware-software design. It requires a lot of things, and you will see in my opinion, the different parts of it in this particular slide. Basically, you need to map the tasks and partition them so that each step executes in its most suitable subsystem. We've seen this before, right? So for compute-intensive tasks, you probably want to utilize the host system. For extremely data-intensive tasks, we utilize the SSD. So step 1 actually goes here, and step 2 and step 3 goes here. And then you need to coordinate data and computation flow to reduce the communication overhead that you have, and to also reduce the writes that you have to the flash chips, because flash chips wear out as you keep writing to them. They have a wear out or endurance problem, and you want to minimize those writes. You could do that by coordinating data flow. And then we designed storage-aware algorithms so that we can actually utilize the SSD bandwidth, flash memory bandwidth, very well by streaming as much as possible. So this consists of usually eliminating random accesses and maximizing streaming access as much as possible. And then we design accelerators, this hardware acceleration essentially, so that we can accelerate some very intensive tasks next to the flash chips over here inside the SSD controller. And also the goal in designing the accelerator is to minimize the impact, meaning SRAM and DRAM buffer spaces that you have over there. And finally, you need to actually be cognizant of how you change the flash translation layer. So we have data mapping schemes and specialization mechanisms so that we can specialize to the characteristic of metagenomic analysis while we can leverage the SSD's full internal bandwidth. There's a lot here. Clearly, every step actually has implications, but you got to read the paper for more detail, frankly, since we don't have time, right? But this is another example that I wanted to provide because it's such an important application going forward. And also, it's a really nice example of algorithm, hardware, accelerator co-design, again, from the across the stack. So we evaluate this with many tools and compare to both software and hardware. I'll just very quickly give you basic results. In the end, you get pretty good benefits, basically, by doing things, partitioning things appropriately between the host and the storage. So these are some performance optimized versus accuracy optimized baselines, and compared to especially accuracy optimized baseline, this in-storage processing gets a lot of performance, more than 14x, without losing accuracy. So the performance optimized baselines usually lose accuracy in the genomic analysis, which we don't want to do in many tasks. Sometimes you can tolerate it, but sometimes you cannot. Okay, so there's a lot more results you can find. We have comparisons to processing in memory also, and processing in storage in this particular case performs much better. But I think in the end, you really need to combine these approaches. You need to combine processing in memory as well as storage. And that's kind of what the future work is going to do, in my opinion. Okay, so there's also a lot of reduction in energy consumption, as you can see. The energy consumption is not as much compared to PIM, but it's still around 2x, as you can see over here. And this is, again, not a fair comparison because this processing in memory baseline is losing accuracy, whereas Megis is not losing accuracy. And if you want to know more about that, you got to read the paper, because why do we lose accuracy? Don't we lose accuracy? Because we use algorithms that are actually not sampling things so that we don't lose any accuracy compared to the baseline version. Okay, I should also mention this. So system cost efficiency, we do a cost analysis over here, and this is one example of the cost analysis. So basically, you may have a cost optimized system with a cost optimized SSD, cheaper SSD, and smaller DRAM. And you may have a performance optimized system with a much faster and expensive SSD and much larger amounts of DRAM. And this basically compares things. So this is the performance optimized, this is the accuracy optimized software baselines. Now if you actually pay a lot more money and design a baseline performance optimized system, you gain some performance, clearly, that's good. Accuracy optimized doesn't gain a whole lot of performance, but it still gains performance compared to here. Now if you use Megis on top of a cost optimized system, you actually outperform both, essentially outperform the expensive baseline system. So basically doing in-storage processing with a less costly system, smaller DRAM and cheaper SSD with lower bandwidth is much better than using an SSD that's much more expensive with a lot of DRAM without doing in-storage processing. I think this is one of the benefits of really thinking about memory in a different way, right? If you keep scaling the system by adding more cost, adding more bandwidth, adding more DRAM, there are just limits because you're still bottlenecked by this data movement. But if you actually have a simpler system, cheaper system, that you don't pay a lot for, but you do in-storage processing or in-memory processing, you'd be much better off, in my opinion. So basically, this also, I think, this is a beautiful analysis, in my opinion, that shows that scaling the system as with business as usual, as we've been doing today, is not a good idea, because you pay a lot of cost for not a lot of benefit. There's another way of doing things by pushing computation to the memory side. Okay, there's more in the paper. There's more in the paper I'm not going to talk about. You can find it, and we open source it. There's a lot more that can come. And if people are interested in doing bioinformatics, this is a fascinating area, in my opinion. There's a lot more to be discovered. This is just genome analysis, just one part of it. There's protein analysis. There's a lot more over here. Okay, I should also mention that one of the tools that we use is really simulation of storage systems, and this is one simulator that we have developed. It's being used by many people across the world, but if you're interested, again, we'd be happy to support it. We still haven't released a new version of this yet. At some point we should. It's kind of messy. Okay. Any questions? Yes?
Could you remind what is the arithmetic operation that we do in genome analysis?
Oh, I mean, it depends on what you accelerate, but usually these are not complicated operations. Usually what you do is comparison operations. It's not floating point multiplication, for example. And genomics is very much simpler in terms of computational complexity compared to multiplication. Yeah. Usually it's some bitwise operations or comparison operations, string matching operations. Yes?
You said SSD have a limited number of writes to the strips. how much worse is the durability of those chips when you do something like this?
So we analyze that in the paper. So if you actually use your DRAM intelligently, you buffer all of those writes inside the DRAM in the SSD. And that's, existing SSDs try to do that as much as possible. When you're dealing with memory that has a wear-out problem, the best you can do is use another memory that doesn't have the wear-out problem and stage all of your writes over there before you write to the memory that has the wear-out problem. Yeah. Okay, so let me also mention that one thing that you do whenever you design processing in memory systems is deciding what to execute where. Because in general, executing always in memory is not a good idea. Executing always in the processor is not a good idea. You should really decide. And one of the difficult things, this is one of the difficult things for programmability as well. Who should do this, who should make this decision? And we actually have been building tools to decide what to execute where. I'll very quickly mention one of them. This is actually a simulation framework as well as tool. If you're interested in processing near memory, I would suggest using this simulation framework as well as the tools. And the goal was to decide, there are a lot of case studies that show that actually near data processing is great, and I'm going to show you even more, but who should decide what should execute where? So in this work, Geraldo, my PhD student, did a lot of hard work to analyze lots of applications. As you can see, it's more than 300 applications on real processor-centric systems, like using Intel vTune, for example, or perf framework. And you can see there are many interesting things over here. He actually analyzed more than 77,000 functions. And he wanted to understand what makes a function more fit for near data processing versus compute, and what is the bottleneck of the function. So it's really a bottleneck analysis mechanism. Without going into a lot of detail, he came up with 3 major metrics. One of them is arithmetic intensity, that you know, flops per byte, let's say, or ops per byte. The other is misses per kilo instruction from the last level cache, if you're profiling this on a CPU. And the other is a new metric called last to first miss ratio. Basically, what's the ratio of miss rate between the last level cache and the first level cache? Because this gives you an indication of the working set size. And this is a very simple, relatively simple to compute metric for working set size. And based on the values, thresholds that these different metrics would take, we came up with basically 6 different memory bottleneck classes. And if you fall into this place, your DRAM bandwidth bound in that function. Here, your DRAM latency bound. Here, your L1, L2 cache capacity bound. And then I don't want to read everything, but here, your compute bound. So basically, your bottlenecks are different based on the profiling that you do in the function. And this profiling can be done statically or dynamically. And you can read the work for more details. So you can actually do this profiling yourself. Now then the question is, of course, if you know this bottleneck, what is the right thing to do? That's another different question, basically. It's not a perfect answer. If you're compute bound, you should probably stay in the processor with good caches. If you're DRAM bandwidth bound, the answer is very likely you should push things to a near memory processor. But the answer actually changes depending on how many threads you're executing, etc., if you're in between. In most of these cases, you're actually better off pushing the function to the memory side. But not in all cases. For example, L1, L2 cache capacity, you may be actually better off pushing the function to the L3 cache. So, but this is one way of actually getting to answer the question, where should I execute this function? There are multiple other aspects of it. We actually improved this work. I don't have the slide, but I'd be happy to talk more. Our goal is to really automate this going into the future. So there's a lot of room for research over here, actually. Okay. And this is all open source. If people want to really experiment with this sort of thing, processing near memory, you can download it, you can use it. I know there are a lot of people using it because there's a lot of activity on GitHub, asking questions, etc. And we'll try our best to actually answer questions. And you can find a lot more information on Geraldo's talks. And as I said, Ramulator 2 is actually being integrated with this sort of thing. If you're interested in contributing to the GitHub of all of these, we're happy to take any contributions. Okay, so I think I can cover a lot more, but I want to move into adoption issues. In the end, I've shown you a lot of examples of near data processing and also processing using memory. And hopefully it's clear that we're really rethinking across the stack, right? There's no simple way of taking advantage of this easily. You need to do some hard work. As I mentioned to someone yesterday, there's no pain, no gain. You need to put some pain so that you can gain something out of it. But I believe the benefits are significant enough so that you can actually, we should put the effort at this point. Hopefully I motivated you earlier also. I believe we can get there step by step because there are some things that you can do relatively easily. For example, if you remember the row clone operation, that's really, really easy, and I think we should really move toward that. What's limiting us? I think what's limiting us is really mindset, in my opinion, and we can discuss this more, but if you think about it, computing has been processor-centric for 80 plus years. Every class you've taken has made the assumption implicitly, and sometimes explicitly, usually most of the time implicitly, that everything is processor-centric, right? And if we're really going against that current over here, you're swimming upstream. It's a good cause though, don't give up basically. Okay, so there are more resources. Now I'm going to jump into adoption challenges. And then we're going to talk about some real processing in memory. So adoption is really key in the end. You can design any hardware. Hardware design, in the end, it's hard. I would argue that's simple. In the sense that you can design it, but finding users for your hardware is the hard part. You can come up with the most sophisticated hardware and no one will use it, and you will use it yourself and it'll be useless in the end. Perhaps, depending on what you do, of course, right? But usually that's the case. In fact, how many people know Professor Arvind from MIT? His picture was earlier. He passed away this year. He taught a course in ACACES in 2013. So I attended his lectures. He attended my lectures during that time. And in fact, Arvind designed some data flow hardware in the 1970s. And he gave a keynote talk at ISCA in 2005. And I was a graduate student at that time. And I attended his keynote. And his major message in that keynote was the same thing. He basically said, we designed this beautiful hardware, it can execute in a data flow manner. What we should have really done is focus more on software to enable people to actually use this hardware. And over time, of course, data flow became bigger and people are now developing the software models to take advantage of data flow, especially because of machine learning today. So if you don't know Arvind, take a look at his papers also. Okay, so basically we need to enable adoption. In the end, adoption is actually not easy. It's a lot of applications and software. What applications benefit, what software benefits. That's why we've been doing a lot of these studies to see what kind of software benefits. I'm going to show you even more without going into detail. How to ease programming. We talked about that yesterday, right? What kind of interface do you have? What kind of compiler support do you provide for programming? That's important. System and security support. We did not talk much about that, although we did mention mapping, etc. But there's more here. Coherence, synchronization, virtual memory, isolation, communication interface. How do you enable that? And there's a lot here. These are all actually extensive research topics, as you will see some examples of. Again, very quickly. How do you design data mapping mechanisms so that you can actually map the data so that it can be processed nicely, processing in memory? And if that data is also going to be accessed by the CPU, how do you actually provide both views of data to the CPU as well as the memory or some other accelerator, right? This is not an easy problem. None of these are easy problems in the end, but they're solvable, I think. And there's more over here, as you can see. And finally, infrastructure. That's one of the reasons why we're building a lot of infrastructure to enable easier access to these things for people. So I think all of these are solvable, and all of these we need to do research on. In my opinion, the hardest part is the mindset. So if you think about, I'll very quickly mention this because we don't have a lot of time, but the mindset of computing industry has been processor is processor, memory is memory, and memory can only give you data and cannot do anything. That mindset needs to be broken. And I think we're at a point where people are breaking that mindset. That's good. Maybe 10 years down the road, that mindset will be completely broken. In academia, we should be even more open-minded. Whenever you see a paper, for example, or anybody sees a paper that basically challenges the status quo, that's a good thing. If it basically says, okay, I'm going to remap the data completely, the first reaction should not be, oh, but that's not good with today's systems. Well, we're not writing papers for today's systems, right? We're writing papers for 20 years later, maybe. So that's the mindset that I'm talking about. Okay, so let's take a look at, well, I'm going to go into the, so I think this mindset is changing. that's why we're seeing these processing in memory prototype examples. But I'll go through relatively quickly some things to make things adopted. And we were actually very interested in adoption from the very beginning. At the same conference where we published the Tesseract paper, which is really changing the entire system, right? We also published a paper that is called PIM-enabled instructions. And SIMDRAM is an example of this PIM-enabled instructions. I'll quickly mention this example. It's a bit old, but I think it's really important to have this mindset for adoption. So our goal was to basically get processing in memory adopted. We wanted to develop mechanisms to get the most out of near data processing with minimal changes to software, no changes to the programming model, and with minimal cost as much as possible. And basically the idea we developed was very simple. Expose essentially each PIM operation as a cache coherent virtually addressed host processor instruction. It's called a PEI, PIM-enabled instruction, that operates only on a single cache block. Because if you operate on larger cache blocks, you cause problems with coherence, because coherence operates in the cache block granularity. And you cause problems with virtual memory potentially also, because now you may need to actually translate many things for a given instruction. That's not very compatible with existing virtual memory and coherence mechanisms. So if you, for example, this is a PIM-add instruction. This is what the programmer does, and this is what the ISA instruction looks like. So this is good because you don't change the sequential execution or programming model, very much like SIMDRAM, but SIMDRAM came later. No changes to virtual memory. SIMDRAM needs changes to virtual memory. No, minimal changes to cache coherence here, and there's no need for data mapping changes here. So this operates nicely with the data mapping that happens in existing processors, because you're restricting each instruction to a single memory module. And then the second idea is dynamically decide where to execute this instruction. Do you execute in the CPU or do you execute in the near memory processor? And here we have a simple prediction mechanism for that. Again, I don't want to go into the details a lot, but here is what we were envisioning at the time. This is again PageRank. If you look at how things operate, this is a processor-centric code. Basically, you bring 64 bytes of data and you write back 64 bytes of data. Essentially, it's 128 bytes that you're communicating, let's say, between processor and memory to execute this instruction. You may say this is small, but if you do it many times, it's actually a lot. Now, if you change this to a PIM-enabled instruction, you can just simply send the value. This is the PIM-add instruction over here, and the value can be very small. It doesn't need to be a cache block, basically, right? It's really 8 bytes only. So you're reducing the bandwidth by 16 times in this particular case. So that's the goal. So the benefits can still be large, even though the changes are relatively small. Okay, so, and then the question is, does doing this in memory always a good idea? And not necessarily, right? This is actually some graph processing applications that we were looking at. And we found out that in some cases, if you actually do this, push everything to memory, you get a lot of benefit. In some cases, you actually get performance loss because in these cases, essentially caching is very effective. The data sets fit in memory, and you have increased memory bandwidth consumption by actually putting stuff to the memory. This is why you need to be intelligent about where to execute things. Okay. So this is an example of PIM-enabled instruction. Again, I'm not going to go into the details, but you can read the paper. But these are some other example instructions that you can add. In this particular work, we targeted some workloads. For example, we have hash table probing to enable hash joins in databases. We have histogram bin index instruction. We have Euclidean distance, dot product, etc. to support some machine learning and clustering applications. Okay, I've already said a lot of this. But there's a simple programming model that people are used to. People are used to doing processing, doing add instructions, and we just changed the add instruction a little bit. People are used to adding fences to do ordering, and we add another fence for ordering. Okay, the key to practicality of this is really single cache block restriction. This is also the curse of this, meaning that it's going to limit our performance. Because we can operate, update, or change, do changes to only a single cache block at a time. We cannot do very wide execution like we've seen in SIMDRAM, MEMDRAM, right? But I think we want it to be basically completely simple in this particular case. Now, these are the changes that you need to do. This is 3D stack memory again. We have a processing in memory execution unit, PIM computation unit, and then, or PEI computation unit. And then we have another PEI computation unit over here that already exists actually. If the add is shipped over here, it gets executed here. If the add is not shipped, it gets executed here. And then we have mechanism to decide what should execute where. Again, this is a very simple directory. You basically query it. The predictor says, oh, it's likely that this thing is in the caches, so execute in the processor, right? Okay, so the evaluation results, very quickly, again we simulate this and we look at some interesting applications at the time, and we see significant benefits over here. You get, especially on large input data sets, you get 47% average speed up. Even with small input data sets, you get about 30% speed up, and you get 25% average energy reduction in a single node. Again, these are nothing close to what we've seen earlier, like 10x, etc., but we're not changing the system a lot. So it's good to think about these adoption mechanisms. Again, I'm going to skip some of these slides because we don't have a lot of time, but feel free to ask questions over here. These slides basically show that if you have large data sets, executing everything on the PIM side is actually good, but if you actually are more careful, you can get a little bit more performance benefit. So large data sets are a good fit for processing in memory in general, because you reduce the amount of off-chip transfer by pushing things to the memory side. If you have small data sets, you should probably stay in the processor, basically, as you can see. If you push things into the PIM, you'd lose a lot of performance. But if you're locality aware using our heuristics, you gain a little bit of performance in some cases and lose very little. That's good. So our decision mechanism is working, basically. The difficult part is really the medium data sets. In medium data sets, sometimes you should execute on the processor's memory side, sometimes you should execute on the processor side, and you need to make the decision making accurately, and we kind of do an okay job, as you can see over here. This is the locality aware one, and this is the blue bars are the PIM only one. So we are better in most cases than PIM only. And this is the energy consumption, so even, especially in large data sets, you can see that the energy consumption is significant. But in small data sets, the energy consumption is very little if you're, when you're locality aware. Hopefully this is interesting, yeah. I think these are some of the fundamentals. I like this paper because it really shows what are the really key issues. It talks about programming, it talks about where to execute what, and it really shows with simple examples the real trade-offs that you need to make in a system. The trade-offs become more complicated, of course, if you have many places to execute code. Okay. So there are clear advantages to this. This is very good for adoption in general over here. But in the end, it doesn't take full advantage of the PIM potential. I think this is, in my opinion, is a small going to the bigger processing in memory execution models. In the end, we will need to take full advantage so that we can get the large performance and energy benefits. So we don't want to restrict ourselves, but for adoption purposes, we may want to restrict for some time. Yes?
Could you get the compiler to like vectorize your PIM add instructions, and then you probably would reduce that disadvantage?
Yeah, absolutely. That's a great, basically the question was, can you get the compiler to vectorize so that you could actually pack a lot of add instructions or some instruction so that you can reduce the restriction of single cache block? And I think that's a great idea. We didn't think about that idea, but I believe it's actually a good idea to explore potentially. Yeah, by vectorization, by making more use of a single cache block, I think you can do a lot better with these. Okay. So how to use programmability, this is something that we discussed. This is a work that we did with NVIDIA. I'm not going to talk a lot about this, but I will mention that this is what we were envisioning at the time. You have a main GPU that's extremely powerful, like today's GPUs. And then you have 3D stacked memories that are connected to it. This is kind of what's happening actually today. Except we wanted in the logic layer simpler GPUs also. So if you have simpler GPUs over there, in the main GPU, if you have very, let's say, code that can benefit from near data processing, you can offload it to the simpler GPUs. And in this work, our goal was to be completely transparent to the programmer. We didn't want programmer to manage anything. That's why it's called TOM, transparent offloading and mapping. So transparently to the programmer, we did data mapping so that you could actually localize the data that a warp is executing on and ship a warp, again, dynamically through compiler and runtime approaches. So the compiler determines which warps can benefit from being shipped to a simpler GPU in the logic layer because it's operating on very data-intensive code, and it's maybe it doesn't maybe require a whole lot of parallelism that main GPU supports. And then basically it gets, the runtime decides dynamically whether it should really be shipped, because there may be oversubscription in the GPU over here, right? You may not want to ship the code that the compiler thinks should be shipped, because dynamically you have a different view compared to the compiler. So if you do that, again, you get about 40 to 50% performance benefit on real GPU type of applications, which is not bad. But again, we're not talking about 10x or 13x, right? But this is again very simple. It's simple changes to the memory mapping mechanism and simple changes to the compiler and dynamic scheduler that is there in the GPU. Okay, there's more in how to use programmability, but I'm not going to cover that. I will mention SimplePIM. This is interesting, I think, but maybe we'll get to that later. The move I already mentioned. So coherence. When you actually execute near memory, what if the data is cached in the CPU? This is always an issue that comes up, and all of our papers cover this in some way. But if you actually do the wrong thing in coherence, meaning you try to satisfy coherence in a fine-grained manner, that's not good, because that actually causes a lot of communication between the near data processor and the CPU. Because you have to check whether every single cache block is in the cache or not. And for that, if for example you ship some code far away to the near memory processor, if the near memory processor now needs to go back to a directory to check whether it can actually access that code and update that data element, that's very bad, because now you're causing a lot of coherence communication back and forth, and we wanted to eliminate all communication to begin with. So you need to handle coherence in a careful way, and a lot of our papers cover that. In many cases, you can get away with coarse-grained coherence, meaning offloading a coarse-grained chunk of data and code to the near memory processor. But if you're doing fine-grained partitioning of code and data, then you may actually need some coherence mechanisms. And we have developed some coherence mechanisms. I'm not going to talk about that in detail, but you can find more information in these papers. So this paper and also this paper. It's a fascinating problem. There's more to be done. I'm not fully satisfied with these solutions. Synchronization, this is actually an important problem also. My PhD student, Christina, did a lot of work in this area. I'd recommend taking a look at it. It's very nice, I think. We need to provide essentially synchronization primitives so that programs can execute on the memory side, right? Okay, virtual memory. This is something that we have not solved yet at all. Oh yes, there's a question, yes.
A question to the cache coherence.
Yeah.
Did you have made an analysis? What's the chance when you're doing an in-memory computation? What's the chance that the next instruction you're doing is also in memory? So, like a chance to say, okay, we have now done in memory, and probably the next instruction will also be capable to perform in memory. So, has there been an analysis, because it could maybe help with the cache coherence problem to just invalidates the cache and
So I didn't quite understand the question. Basically, you're saying when you're executing in memory, what's the chance that you're going to touch something in the CPU next?
When you're processing data in memory, did you have made an analysis to say, okay, we have now worked on this in memory, and the next instruction we're doing is potentially also in memory. So based on the complexity of the instruction, is the next instruction also?
I see. Yeah, we have done a lot of analysis, and basically what's the communication between the instructions you're thinking, I think. Yeah, we have a paper called ALP that I didn't mention over here, but it really tries to look at like what is the data flow between the instructions. It tries to ship not just instructions, but coarser granularity, let's say data flows to the memory side. And that actually reduces the coherence overhead, but only if you actually design your coherence mechanism to reduce the coherence overhead, right? Okay, these are good problems to think about. So virtual memory is actually a mess. Virtual memory is a mess in processor-centric systems also. Basically, the problem is you provide virtual memory, and it provides a nice abstraction for programming to the programmers. They don't need to worry about physical memory management at all. Unfortunately, if you ship something to the memory side, now you need to provide that abstraction also, assuming you want to support virtual memory over there. Now this means that you need to replicate the virtual memory translation structures and access protection structures on the memory side. And this is expensive, clearly. Now this whole thing is very expensive. Virtual memory was invented in the 1950s, and we're still using essentially the same mechanisms. So we need to completely rethink virtual memory. After 60 years of, let's say, or more than 60 years of processor design, we're still using the same abstractions, which I think is pretty bad. But that's a different lecture. I'd be happy to talk about virtual memory later on. We have some works on that topic. In the end, virtual memory complicates a lot of things, not just processing near memory, but also other things. Even GPUs started supporting virtual memory more recently, right? They didn't have virtual memory to begin with. But this is an issue that you need to think about. Okay, evaluation infrastructures we've talked about. So there are other things. I'm going to skip the slide, but you can see this is another way of thinking about the challenges, compilers, operating systems, etc. Let me talk about the framework that we have designed recently. I think this is one of the, like MIM-DRAM was a way of increasing the abstraction level to provide programmability. This is another way of increasing the abstraction level to provide programmability. And here we're going to resort to things that we know of. So basically, we were inspired by existing hardware that I'm going to talk about. Basically, today you have hardware from UPMEM, for example, you have processing in DRAM. And unfortunately, programming is challenging. It's relatively easy, but still challenging, in the sense that you need to distribute data across memory banks, parallelize the execution, manage data transfer between host cores and processing in memory cores, and manage data transfer between processing in memory cores and DRAM bank and the PIM scratchpad. This will become more clear later. And you need to launch kernels and you need to synchronize properly. So if you do this at the low level, it's not easy for all programmers. So in this particular work, we actually provide a high-level programming framework for real PIM hardware. You can actually download this framework, buy the system from UPMEM, or talk with us so that we can get you access to UPMEM systems, or talk with them so that you can get access. And then we actually test this programming framework. Basically, we provide higher-level iterators like map, reduce, zip, that are clearly used, broadcast, scatter, and gather for communication primitives. And in the end, we implement these on interesting workloads, and we find out that you can get both better performance than hand-optimized code, and also simpler, let's say fewer lines of code compared to hand-optimized code. I think this is interesting, and we should really be working on this sort of thing going into the future, among other things. But programming is really important. Okay, I'm going to skip this because I already told everything that this says, kind of. But if you have this high-level framework, then you can also couple it with compiler optimizations. So we actually use this high-level framework to go through a compiler and do all of these optimizations. Maybe not in the best way. If you do more, then you can do better. Perhaps you can do vectorization, for example. But unfortunately, I think UPMEM's current cores don't support vectorization internally. Okay, so there's more in the paper. You can really download it and test it for yourself. And this is an example of the code that you need to write, histogram example, not the full code. And we simplify it to be much nicer and cleaner, let's say. And if you want to look at some quantitative data for different kind of kernels, we can have significant line of code reduction, as you can see over here. And the performance improves also, so that's the good part. Not for every application, but for a good fraction of the applications, you can reduce the lines of code and also improve performance at the same time. So there's a lot more to do in this area, I think, and not just on real processing in memory systems, but also for future processing in memory systems. Okay, questions? I'm going to skip this one because we've already talked about that. So there's a lot more. So as I said, we need to also look at applications and software. We need to accelerate more. I'm going to very quickly go over a lot of works that we have done. There are also other works that other people have done to show benefits from processing in memory. So the evidence is actually increasing, right? That you can do a lot with processing in memory. So we've accelerated pointer chasing in 3D stacked memory. We've accelerated actually transparently cache miss processing, if you will. It's more than that, but you can look at it. We've accelerated my PhD thesis. In the memory controller, you can actually do prefetching, like using run-ahead execution. This is a much better way of doing my PhD thesis, in my opinion. In my PhD thesis, we basically speculated in the processor to execute instructions when you stalled otherwise. Here, what we do is, if the processor is going to stall, why don't you ship the code speculatively to the memory controller, and the memory controller does the prefetching for you, and the processor can keep going on executing the main program while you're doing prefetching for the program in the memory controller. So this is actually a really nice way, and it actually increased the potential of prefetching much better. We've looked at accelerating climate modeling using FPGAs. I'm going to talk about a version of this later on very quickly again. Clearly accelerating DNA read mapping. This is actually a very interesting paper. It changes the representation of the genome so that we can actually do much more parallel processing in 3D stacked memory. It's a relatively early work in that area. Accelerated approximate string matching. Somebody was asking what are the primitives in genomic analysis. Approximate string matching is one important primitive to compare different genomes. It's important. We've also looked at accelerating sequence to graph mapping. So there's actually, in genomics, there's also graph analytics involved, which is really interesting. Well, there's more, but I don't have time to talk about a lot of these. Time series analysis is very interesting, actually. This is something that's employed. So basically, you're really analyzing huge amounts of streaming data coming from, for example, satellites, astronomy, etc. And you want to look at anomalies in the data. And people have developed beautiful methods called time series analysis, and there are multiple algorithms here. And this is actually a very data-intensive task, and we developed accelerators to accelerate this. And you could do this in near memory processors, and you could also do this using non-volatile memories. Okay, I already talked about this. Database systems are actually a very good example of processing near memory. We have another, especially hybrid transaction analytical databases are things that can do both processor-centric code and also data-centric code. You can take a look at that. Very interesting. We've already talked about ML inference. We already talked about this. Okay, I'm going to talk about this later on when we talk about real memory systems. So in the end, I think these are all, our goal in looking at all of these was really to understand what we can accelerate and what kind of software would benefit. So basically, does PIM make security worse is another question, right? Clearly, we can make it better or easier by doing random number generation, etc. But worse is also important. And there are many interesting questions here that I'm not going to cover. It's also a research topic. So in this work, we use the UPMEM system to look at homomorphic encryption operations. This is going to be a lot more important in the future. I think actually processing using memory is a really great fit for homomorphic encryption, but I'll leave it at that. And we also looked at what happens to side channels in processing using memory and processing in memory systems. And I think it's also an area that requires more investigation. In my opinion, and also I delivered a talk, so there's a talk over here that's kind of futuristic. You can actually look at it if you're interested, but I don't have time to talk about that. Basically, I think processing in memory, I believe actually processing in memory can make security much better, as I said yesterday, because it reduces the side channels in the end overall, especially if you move a lot of security critical things on the memory side. So now, before we move to memory robustness, I want to cover things that are happening in the real world. So if I was giving this lecture in 2019, none of this would be here. And last time I gave this lecture in 2018, clearly none of this would be here, because 2018 precedes 2019. Happened before relationship, right? Distributed systems, it's important. Yeah. Okay, so I should say that I'm not going to cover a lot, but we have a lot of tutorials, especially focusing on real processing in memory systems. Some of them actually have talks from SK Hynix, Samsung, Alibaba, people who actually built these systems. And we've organized these tutorials online. There are also hands-on labs also. You can do programming on the UPMEM system, for example. You can find all of these information online. Everything is on YouTube, etc. And these are some individual links if you're interested. And we're holding one at Micro this year. Before I go into UPMEM, etc., I should say that near memory processing engines existed even before UPMEM, except in a different way. So this is a paper that we wrote that exploits something that looks like this. We worked with IBM on this. Essentially, IBM had a flexible interface called OCAPI, which is very similar to CXL today. With some differences, but no fundamental differences from my perspective. It's a flexible interface that can enable you to offload things to stuff that's far away from the CPU. And one of the things that you could offload things to was an FPGA board with high bandwidth memory attached to it. So basically this is an FPGA, and inside the FPGA you can reconfigure things to be so that you can actually take advantage of the high bandwidth memory that's directly attached to the FPGA. And we did this for weather modeling, climate modeling, and genome analysis applications. And again, without going into a lot of detail, we saw significant performance benefits on this real system. This is a real system. The benefits you get are basically you do near data processing clearly, and you can also reconfigure the FPGA so that you can actually accelerate the hard part of the computation at the same time. And you can see the performance and energy efficiency benefits on real workloads. This is nice, I think. But this is what you can do today. I think going forward, these things are going to be even more common, especially with interface like CXL. I'm going to show you a paper by SK Hynix in 2023 that does essentially the same thing on their CXL-based prototype. Not on these applications. These applications are a little bit different. They did it on databases. Okay. So this is the UPMEM engine that was introduced in 2019. As I said, it's a French company in Grenoble. You can talk to them. We'd be happy to help if you're interested in getting access. We're working a lot with them. Essentially, they introduced these DIMMs. These DIMMs look like real memory DIMMs, right, existing DIMMs, except inside each DRAM chip, you have processors. Now let's take a look at what those processors may look like. We have a lot of papers. If you're interested in a paper, I'd recommend reading this one. This is a very long one that analyzes it and describes the programming, etc. Oh, okay, I don't have a very good picture. Where's the picture? Oh, sorry. Somehow, all of my slides decided to delete one of the pictures. Okay, but the picture. Okay, now imagine the picture. You have memory banks. Each DRAM chip, in this particular case, has 8 memory banks. Next to each bank, this is a DRAM chip we're talking about within the DRAM chip. Next to each bank, you have a processor. And this processor is a multiple instruction, multiple data, fine-grained, multi-threaded processor. It's really a processor, basically, general purpose processor. Now, this is very nice, meaning that you can actually offload any code over there. Theoretically, you may not get performance because processor has some limitations. The processor, so what are the limitations? Limitations are that, well, what are the benefits? Benefits is you can minimize the data movement, right, because you're right next to DRAM, each DRAM bank. You can also reduce the energy of your program, and you can parallelize across different DRAM banks. You have lots of processors operating across different DRAM banks. So if your program can be parallelized nicely across DRAM banks, if you map your data, this is actually great. Now the limitation is that the processor over here cannot be as powerful as the processor in your CPU, because this is DRAM process, and DRAM process is really customized for capacity in general. And this is very bad for logic processes, very different from logic. As a result, when you implement logic in the DRAM process, it becomes very leaky and slow. So this processor occupies a lot of area, and also it's slow. It's about 350 megahertz. I think UPMEM is increasing it to 450 megahertz. But it's nowhere, not anytime soon it's going to go to 2 gigahertz, for example, because this is the DRAM process. That's the downside of actually incorporating logic inside the DRAM process. 3D stacking technology solves this problem, except 3D stack technology has a thermal problem, right? So you cannot escape the trade-off space in the end, but you can change the trade-offs a little bit. So the other downside of this is you cannot communicate easily between cores across different banks. Even though you're in the same chip, there is not enough interconnect between cores. And the reason is, again, this is DRAM process. DRAM process is optimized for cost, and DRAM folks don't want to add more interconnects. We want to change that mindset. This can be solved by adding more interconnects and by changing the process. This is easier, I think. The first one is a lot harder. But because of that limitation in the existing system, whenever you want to communicate between one PIM core in one bank to another PIM core, you have to go through the processor. Processor meaning the CPU. Very bad thing, right? You don't want to do that at all. We wanted to eliminate all of that communication to begin with. And the other thing is more, there are some design choices over here that I don't want to pick on, but the instruction set doesn't support multiplication instructions that are larger than the granularity of 8 bits. So the best you can get is 8-bit multiplies. If you want to do 16-bit multiplies, it's a lot more costly. If you want to do bigger multiplies, good luck. So basically, this is not good for especially workloads that exercise multiplication a lot. And there are some workloads like that, as you may guess. Like machine learning, right? But of course, if you reduce machine learning to so that your multiplications are smaller, that's a different thing, right? Okay, so I've given you basically the basics without showing you a picture, but I'm going to add the picture in the slides. I keep updating the slides on the website, so if you download the slides, you will see them. So we did a lot of analysis, and we found out that fundamentally, because of the reasons that I said, low frequency, etc., and not a lot of operations supported, fundamentally, this is compute bound. This engine is compute bound, which means that the memory, most suitable workloads are memory bound, as expected. And we actually provide the benchmark suite, and in this benchmark suite, we showed that some workloads actually gain a lot from the UPMEM system because they're very data intensive and they do very simple operations. Essentially, the most well-suited workloads are use almost no arithmetic operations and use simple operations. And there are a bunch of them, like scanning in a database. Could be genomics is another example over here. I'm going to show you one example. But there are other workloads that actually do pretty bad, like matrix vector multiplication, etc. Okay. So you need to decide what workloads benefit. And also, I think the workloads that are well-suited require no or little communication between the processors across different banks. Okay. So if you're interested, this is a short paper that summarizes it. And this is the workloads. People actually use this workloads to benchmark processor-centric systems. It's all open source. If you want to get into the research over here, it's relatively easy, I would say. In fact, folks from ACACES in Korea, they wrote, as I mentioned yesterday in one of the things, in my first talk maybe, they wrote a beautiful paper analyzing the system, building on top of our work, and it got the HPCA Best Paper Award, their paper. I like that paper quite a bit. And again, there are more papers, and you can see Juan's talks as well. So we wanted to also look at other applications in this system, and one of the tough applications is machine learning training. We're not looking at deep neural networks over here, but some other more classical machine learning applications. If you want to get high performance out of this system, you basically need to adapt your algorithms to the hardware, because hardware doesn't support everything. There's no floating point here. It's all fixed point. Meaning if you want to do floating point, you need to change your data representation to fixed point. Basically to optimize performance, we use fixed point, quantization, and hybrid precision in this particular ML training workloads. We use a lot of lookup tables to implement complex functions in this particular case, because you cannot have complex computation in the DM. One of the reasons they went with 8-bit multiplication is because 16-bit multiplication is expensive, right, in terms of area. And complex functions are even more expensive. So you need to actually approximate those complex functions in some other way. You need to optimize data placement and layout so that you can actually stream through memory. This is actually what you need to do in all kinds of processing near memory approaches. In the end, we show significant speedups over CPU and reasonable speedups over GPU, even though this is not a fair comparison, I think, because GPUs are much more expensive. And also GPUs have been optimized for many years, right? Okay, so you can learn more about this over here. And this is the paper that summarizes it. We have also looked at more difficult workloads on the system. And we asked the question, can we actually make these workloads a little bit better? Sparse matrix vector multiplication is one of the very difficult workloads on the UPMEM system. And if you're interested, you can actually download the library and improve on it. This is beautiful work. And it basically different 25 sparse matrix vector multiplication kernels. It looks at different approaches like compression, data types, partitioning, synchronization, and load balancing, and a combination of all of those. And it basically analyzes them and compares UPMEM to CPU and GPU systems. In the end, UPMEM doesn't perform as well, because it's expected, right? It cannot do multiplies really well, but its efficiency is much better, meaning it's actually much better able to utilize the memory bandwidth. Meaning if you actually design a near memory processor that is more capable in multiplication, etc., you can do much better than what is possible. And also keep in mind, this is the first real prototype of a processing in memory system. We're comparing this to 80 years of CPU development and 25, 30 years of GPU development. So it's good to always think about the fair comparison. Okay, we have more work that I'm not going to talk about. As I said, we did sequence alignment on real processing in memory system, and we see a lot of benefits over here. This is where UPMEM system really shines, in my opinion, compared to both CPUs and GPUs, because the operations in bioinformatics are usually, at least read mapping or alignment, are relatively simple operations. They don't require multiplication. These are bitwise operations, string matching operations, etc. Okay, I already mentioned this. More recently, we've looked at accelerating reinforcement learning and other ML training. This is actually a paper that's going to appear at PACT this year. And again, this is another algorithm, I don't want to say hardware co-design, but algorithm design so that you can fit the hardware better. I will just read the last sentence. Our results demonstrate the necessity of adapting PIM architectures to enable inter-DPU communication. So you really need to have communication across banks. That's what we're saying over here. To overcome scalability challenges for many ML training workloads. And we discuss decentralized parallel SGD optimization algorithms, stochastic gradient descent optimization algorithm, as a potential solution. So it's very interesting, but I'll leave it at that. We don't have time. We've also been looking at accelerating graph neural networks. Again, these are tough workloads for this system. We're kind of challenging the system with these tough workloads so that we can really understand what are the downsides and what we should do in the next generation systems going into the future. Because current generation, at least from an academic perspective, it's not interesting. From a startup company perspective, you're very interested in that because you're going to make money out of that, right? But from an academic perspective, what's really interesting is understanding these current systems so that we can build much better systems 10 years down the road, right? Okay, and I'm not going to see. Okay, there are other people developing these things. Samsung has a very different approach. In 2021, they introduced this architecture. Basically, they modified the base layer of, essentially HBM. Next to each bank, very similar to UPMEM, next to each bank, they have a processor. But this is not a general purpose processor, it's an accelerator. It's an accelerator that is optimized to do this stuff. Multiply and accumulate. So their approach is completely different. They want to really specifically accelerate multiply and accumulate operations, and you can guess what they're used for, machine learning, right? And you can see they actually have a full design. They have floating point 16 multiplication addition. It's expensive, but it's an accelerator. And this is their instruction set. As you can see, it's a very limited instruction set. UPMEM is very general purpose. And this is their chip, and they write papers about it. This is not unless you have special connections with Samsung, you don't have access to this, but good luck. They've also developed this board with Meta. This is, here they have an FPGA, and this FPGA is configured to accelerate recommendation inference. Recommendation inference happens to be a huge data intensive task because you have huge embeddings in memory, so they have a lot of memory and they have access to that memory reasonably fast. And again, they have papers on this, so I'm not going to talk about this in detail. So SK Hynix also introduced their accelerator. Again, so except for this one, everybody modifies the DRAM chips. So this is something people didn't consider a long time, even 6-7 years ago. Yes?
Everything you've been telling the last half hour or so, in my view, just points out that the DDR interface is a crappy interface.
Yes, yes, we're going to get to that. Maybe doing...
Which is attaching DRAM to a processor. That's it. It has been done for the last 40 years. You're just skipping the DDR interface.
Yeah, exactly. I mean, I have a lot of we have a lot of papers on that topic also, saying that we should really change the memory interface completely. And I agree with you. Yes, interfaces to memory are designed for mainly to supply data to the CPU, and even then they're not designed well. They're actually, we have a lot of legacy. But maybe we can talk about that tomorrow, because tomorrow's robustness lecture also, or today's plus tomorrow's robustness lecture is going to touch into that. So SK Hynix does something similar. Again, this is their talk at one of our real processing in memory workshops. Their goal was to also accelerate machine learning type of applications, so their design is actually somewhat similar to Samsung's. So a company like Alibaba, they also designed their own DRAM chip, if you will. This is their DRAM. Again, we had a talk from their chief engineer in one of our workshops. And their goal was, again, this is also a near bank architecture. So all of these are near bank systems. Basically, next to each bank, you have a processor or an accelerator. And in this case, their accelerator was essentially to accelerate recommendation systems. So they called neural engine and match engine. Again, you can read their paper for more detail, except they don't have more detail in that paper. So this points to the interface part a little bit. Basically, if you look at this over here, people have been thinking about new interfaces to at least free the CPU from the DRAM interface. It doesn't free the DRAM from the DRAM interface, but frees the CPU from the DRAM interface, such that the CPU can have a much more flexible interface to do the offloading. This is the paper that I mentioned. It's kind of similar to what we did with IBM. SK Hynix basically built an FPGA prototype. They call it the CMS card. I don't remember what it stands for. But basically, this has a CXL interface, and the host CPU offloads computation to an FPGA that is near memory, essentially. Okay, Samsung did something similar, but they don't have a lot of detail. You can read more about that. Okay, I could keep going, but this is where I would like to stop and take a step back. And then I will hopefully start memory robustness. Okay, let me conclude. I think hopefully it's clear that we need to design fundamentally energy efficient architectures, and I think they need to be data centric. We need to design a fundamentally high performance architectures, and I think they also need to be data centric. So data centric architectures, memory centric architectures are really common for both performance and efficiency, and also sustainability, I think. And I think also security and robustness, but I don't want to add that yet over here. So we need to minimize data movement in our systems. Now let me take something, let me also talk about philosophy a little bit. A very famous architect said this: architecture should be based upon principle and not upon precedent. Can anybody guess who this architect is? Okay, not a computer architect, this guy. Frank Lloyd Wright. He is basically the, let's say, father of modern American architecture, but also a lot of architecture in general. He was a very principled man, very headstrong, and because of his principles, he didn't design this. He thought this is precedent-based, meaning everybody does this, right? Now let's do something much more principle-based, and this is what he designed. This is one of his masterpieces. Many people consider it his masterpiece. Does anybody know what this is? Okay, you got to visit Pittsburgh. This is falling water, very close to Pittsburgh. It's in the mountains of Pennsylvania, and well, it's close to where I used to teach. So I used to go there a lot. But if you look at this is based on some principles. This is a waterfall, and this thing is really constructed on a waterfall. Water really flows underneath it. And if you look at this shape over here, these cantilevers are actually shaped based on this waterfall. And he has some principles. It's organic architecture anyway. It's not important, but it's based on some principle. Okay. So now that I teach in Zurich, I use this sort of stuff. This is a precedent-based design. Everywhere in Europe, especially in Germany and Switzerland, you see things like this. In fact, this is from Germany, not from Switzerland. But, okay, it works, not bad. This is a more principle-based design. Well, I should say that this is precedent. It's also based on some principle, right? Yeah. It's not principle-less, let's say, in that sense. But this is a different principle. And if you go into here, you feel very different. Does anybody know where this is? This is in Zurich. It's in Stadelhofen. Yeah. This is somewhere else. Porto, if you're from Portugal. There's another principle over here. This is somewhere else. If you're from Valentia, you would know. This is somewhere else. New York. These are all based on the same principle, actually, and common to the same architect. Who could that be? No one Spanish here? There you go, Calatrava. I guess I gave you too strong of a hint. He looks like this. He's actually an ETH alumnus. Yeah, but basically it's based on some principle, and he's a very principled man also. Okay, so basically I should also say this. All of these are much more costly. If you design this, oh, it's very cheap. Processor-centric systems today. These are much more costly. In fact, when Calatrava was constructing this, at some point New Yorkers said, stop, we don't want to pay you more. After $4 billion or something like that. I mean, $4 billion didn't go to him, of course. So it went to all of the construction, etc. But he's still very rich. If you want to be rich, maybe you should be doing architecture in some other level. Yeah, but basically, these are costly. But cost gets amortized over time. So cost should not be our consideration. So once you move to a different mode of operation, you will realize that this is very different. Initially, it's very hard to get there. You have to pay a lot of labor and cost, like moving into processing in memory systems, etc. But once you get there, now that's the mode of operation, that's what you're optimizing. And people who go there don't think about cost anymore. This cost gets amortized. In fact, people pay money, etc. Over time, you actually amortize the cost a whole lot more, and you're operating at a much more efficient mode of operation, hopefully. So that's my perspective over here. That's one of the reasons I showed this. There's also another reason. Have we discovered or are we actually using the overarching principles of computing? So this is a computing device, in my opinion, and it's operating on principles that are very different from how we design our systems today. So I think maybe we should really figure out what are the other principles that you should use in our computing. So computation, communication, and storage are very coupled over here. Okay, so I think concluding this memory-centric computing lectures, we really need to start designing principled system architectures to solve the memory problem, because that's our major problem. We need to be more balanced in our system design, and we want high performance, efficiency, and sustainability. That all requires us to be memory-centric. We need to enable computation capabilities in memory. This can lead to orders of magnitude improvements in performance and energy. I've already shown you a lot of that. This can enable new applications and computing platforms. I strongly believe that like new type of genomic platforms, medical platforms can be enabled using this, and also edge platforms. This probably will enable us to understand nature better also, because I think this is closer to how nature operates as opposed to how we design systems today. So I think the future is quite bright, but we still need to do a lot of hard work. And since you're at the summer school, you may be doing some of that hard work, right? Research and design across the computing stack is hopefully interesting. So I think this is, what we've covered so far is really data-centric architectures, but I think data-aware architectures that we've covered at the beginning earlier has very good synergies with data-centric. I don't know if we'll ever get to cover data-driven. Let's see. Okay, I've already said a lot of these. You can find a lot of open source tools over here. And I should acknowledge the funding because industry, even though they don't move easily, they actually support this research. I should also say that. They're actually interested in really figuring out what they should be doing like 10 years, 20 years down the road maybe. Not everybody thinks that way. Sometimes they think 1 year down the road. But still, industry is actually quite supportive of this. Okay, any questions? As you can see, the title has changed. Oh, I still have time. That's good. But feel free to ask questions. I could tell you more stories about the architectures, plus principles of nature, etc., even though I don't know enough. We haven't discovered that yet. Okay, no questions? Then I'm going to jump into memory robustness. This is going to be another fun topic. It's actually a very, very exciting topic in my opinion. And there's a lot going on in industry to fix this problem. It's not going to be easy to fix. So I've already shown you some examples, right? This is a bridge. Does anybody know where this bridge is? Well, it doesn't exist anymore because this is what happened to it in 1940. This is the Tacoma Narrows Bridge. It's also close to where I used to live in Seattle. Essentially, a bit flip happened. It's a reliability problem. It's called aerostatic flutter. You can actually watch videos of it. It's fun. Now they built 2 bridges, and they're next to each other over there. So there's the principles of redundancy apply in bridge construction also, as you know. Well, actually, bridge construction is very interesting. I mean, very quickly. Robustness problems are everywhere, right? Clearly, I had a lot of robustness problems in my computer earlier, but people have been dealing with robustness problems for a long time. And one of the reasons why wind tunnels become really popular is because of this. Because this bit flip happened, and one of the main reasons was because wind was really causing this aerostatic flutter in this, and they started simulating, simulating the bridges using wind tunnels after this. So if you and wind tunnels actually, because wind tunnel simulations are expensive, that actually catalyze a lot of computing research. If you think about it, people actually start doing a lot of computing research to accelerate wind tunnel simulations. So there's a lot of interesting stories related to this too. Okay, so this is, I've already shown you this picture also, right? These people are sitting on this rod. If a bit flip happens, they're not going to be happy. So I think going into the future, we should take the perspective that we're not safe, we don't have robustness, and we should really design systems to be much more flexible to prevent unforeseen consequences. Now that's a very general statement, right? What's an unforeseen consequence? Well, you don't foresee it. So, but at least maybe you can design soft systems that can actually reconfigure themselves or figure out these problems in the field. I'm going to give you some examples. Okay, I've shown you this picture also, right? This is Mr. Bean. Okay. So what is RowHammer? Look, I think I've shown you this also, but we're going to go into more detail. Essentially, this is the fact that you can predictably induce bit flips in commodity DRAM chips. Essentially, all recent DRAM chips are fundamentally vulnerable. And again, I think this is fascinating to me. This is really the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. Not just security, but also safety, reliability, etc. And clearly, it got a lot of people excited, as you can see over here with this title. I've already mentioned this position paper. I'm not going to talk about that. I'm not going to talk about the DRAM scaling problem, except I'll remind you that the DRAM stores charge in this capacitor, and then you have this access transfer, and everything needs to work well so that you don't get bit flips. As you reduce the size of this, it becomes much more vulnerable to all types of noise. And RowHammer is one type of noise or failure mechanism. And again, I've shown you these pictures. This is a fascinating area. I will also mentioned this in an earlier lecture. We did studies at the data center level, and we found out that if you employ denser DRAM chips, you get more server failures in real production data centers. And again, you can read these studies. There are papers related to it. So we built a lot of infrastructure that I also mentioned to test DRAM chips. And again, this is open source. People are using it. And one of the main reasons why we built this infrastructure was to actually test data retention times. And I've already mentioned this also. This is just to jog your memory. Basically, we wanted to get rid of refresh, which is one of the scaling problems in DRAM. And it's also very bad for energy and performance and quality of service. And we tried. These are the papers that we wrote initially in 2012, and that's the reason we built this infrastructure actually, to test these retention times. And you can read this paper. I'm not going to cover this. It was covered in earlier versions of this course in 2013, 2018. And you can see that people actually find this paper interesting, so they selected to some retrospective issues that was published at ISCA last year. Not only this paper, they also selected this paper. I was surprised that they selected both papers, because this paper is more theoretical, meaning that, oh, let's do this to get rid of refresh. And this paper says, oh, we tried this on real DRAM devices, and you need to work a lot harder to get rid of refresh. And this is really an experimental study of can you get rid of refresh easily. It looks at the data retention times, and it looks at the challenges. It's fascinating, but we don't have time, unfortunately. So we also had an infrastructure. I promised this, I didn't show you this before. At the time we were looking at all of these issues, we also had an infrastructure to test the flash chips. This is again an FPGA-based flash memory controller. So you could attach flash chips to it and test it, and we were writing papers about it, analyzing the error patterns in flash chips. And flash was actually very difficult to scale at the time. This was before flash moved to 3D stacking. It's still difficult to scale, but it became a little bit easier with 3D stacking. Now you can read papers. Intel invited us to write this paper in their technology journal in 2013. And we have a more recent paper that summarizes a lot of the research in this area. If you want to go into flash memory and storage, understand how an SSD operates, this is the paper that I would go to. Okay. So while we were doing all of this, we also asked the question, okay, DRAM, and actually, in fact, in these papers in flash memory, we saw a lot of read disturbance issues. Whenever you read a page in flash memory, you disturb other pages. So some bit flips happen. So you need to design your flash controller to fix those issues. Otherwise, you'll get bit flips in storage. But in flash memory, we have a beautiful interface, meaning that flash controller can be designed to be completely flexible. It can do anything it wants to fix all of these issues. In DRAM, we don't have that interface today because somebody designs a memory controller and it has a very rigid interface. So we actually did a lot of studies to understand this read disturbance. And we asked the question, does DRAM have read disturbance errors also? So together with Intel, we tested DRAM, and we found out that it has disturbance errors. So what's the disturbance error? This is DRAM that you've seen this sort of subarray earlier, right? You have many rows. Now if you want to, each row has 8 kilobytes of cells, for example. You've seen this before. Now if you want to access a data element in one row, you need to activate that row, meaning that you apply high voltage to that word line. You open that row. It's called activate in DRAM. If you want to access some other row, you close this row, or apply low voltage to the word line, or it's called pre-charge in DRAM. Now, completely legally, if you keep doing this repeatedly, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, if you do this enough times, before the DRAM cells get refreshed, it turns out some bits that are vulnerable and physically adjacent rows get corrupt. They go from 1 to 0, for example, or 0 to 1, depending on the encoding. We call this the hammered row, we call this the victim row, and this clearly is something that should not be happening, right? Just by accessing memory, you should not be corrupting data anywhere, because we're not even writing to memory, let alone writing to rows that we're not accessing, right? So these victim rows can belong to your own application. It could belong to some other application. It could belong to the operating system, the page tables. It could belong to, I don't know, some security critical application, some crypto application, right? And as a result, someone can actually do bad things to your system. So we tested DRAM chips from 3 major manufacturers. There are only 3 major DRAM manufacturers in the world. You can probably name them. We're going to name them later on. ABC, let's call them now. SHM are the first letters. Yeah. We're going to talk about that tomorrow a little bit more. But we found out that more than 80% of the modules we tested are vulnerable to these bit flips. Essentially, in the old chips we tested, we didn't observe this phenomenon. We observed this phenomenon in the chips that are manufactured in 2010, and all of the chips that were manufactured between 2012 and 2013 exhibited this phenomenon. Don't focus on the error rates. These change over time, etc. It depends on the testing, etc. But basically, we argued that this is a technology scaling problem, meaning that in the older DRAM chips, you cannot do enough hammerings to cause a bit flip, because cells get refreshed before you could do enough hammerings, because cells are far away from each other and cells are bigger. As cells become smaller and closer to each other, you could cause a bit flip by doing a small number of activations, smaller. And as cells become smaller and smaller, the number of activations you need to induce to cause a bit flip reduces and reduces. So now you can fit activations within a refresh interval. Okay, so basically let's talk about why this is happening. I'm not going to go into the device level a lot, but there are a lot of interesting device level things. I'm going to draw an abstraction level. Essentially, DRAM cells are too close to each other. They're not electrically isolated from each other. Access to one cell affects the value in nearby cells due to electrical interference between the cells and between the wires used for accessing cells. And it's also called cell-to-cell coupling or cell-to-cell interference. A high level, one reason is when you activate one row or word line, apply high voltage, an adjacent row gets slightly activated as well. And vulnerable cells in that slightly activated row will lose a little bit of charge. And if you keep activating, if RowHammer happens enough times, charge in such cells get drained. Which means that you lose the data. You lose the charge, you lose the data. And this is what should not be happening. And this, the bad thing is, if you corrupt data, this is now immediately visible to your data structures. Because this is DRAM, we're talking about main memory. If you corrupt the data, it's part of your data structure. System data structure or user data structure or different applications data structure, right? And this is not good. Let me see how much time we have. Oh, okay. I'll stop at a nice point over here. We basically released this code. Later, people developed on top of this. This is x86 code. What it does is it selects addresses x and y such that it avoids cache hits and the processor avoids row buffer hits. And it basically ping-pongs activates to x and y. And if the chip is vulnerable, you'll get bit flips. And people downloaded this code and actually replicated. You can download this code and try it. Hopefully you're not running something extremely important for your machine. Be careful. But Google actually has a much better version of this code. We're going to get back to this. So we basically said this is a real robustness issue. We were able to show that you could get real errors on Intel and AMD systems using this code. And this should not be happening, right? And there's nothing special about Intel and AMD. People have shown that you could do this on any processor that is a memory controller that can access memory reasonably. If you design a terrible memory controller, you cannot do this, but nobody designs terrible memory controllers today. Okay, I think maybe I'll stop here. This is probably a good place to stop. Otherwise, I'll go for too much. So tomorrow we're going to pick up here, and then we're going to talk about what we can do about it and what this has affected. Probably we're not going to go into machine learning driven memory system design, but we have a lot of slides that you can look at on your own. Or you can talk to me about it if you're interested. Okay, see you tomorrow. Or find me later.